So I invite you for the 7th lecture from Computer Architectures course. And for today's lecture, we will look on the input and output from our computer. And we will practice it with Qt sim. And during the next lecture, we look even at the possibility to use the real hardware, our MZ-APO boards, which you will use for the semestral projects. And if we start, we will start with some review or overview how the input-output is available on the today computers, because it is, you see everything. What are the options for the input-output? Because you want to not only to basically have some computation inside the computer, but you want to interact with it. And today, typical way how we connect the peripherals and map them into the computer system is a memory-mapped peripherals mechanism to mapping them into the address space. Then we look at Qt sim, the examples how we can use our simulator to demonstrate those possibilities, and then we look how it is connected and interconnected add-on boards in real PC personal system computers. Okay, we again return back to the von Neumann concept of the computer architecture, where we know that we have some common memory where we can store program and data. And the program is read and then processed by the control unit, and it sets up a data path which reads data from the same memory. As for the input and output, original idea was that the computer has special set of the instructions which allows directly to the processor to access the input and output. This idea at the initial time has some backup to do it this way. But today you usually want a faster delivery of large data of the network packets and so on directly to the memory, and then audio, for example, again directly from the memory to the peripheral. So the processor prepares data in the main memory and then commands the peripheral to take them over. So that original idea that you will have a fast input-output instruction directly in the instruction set is overcome today. But on the other hand, on some small chips, for example, if you know Cortex-M microcontrollers, which are used in the embedded applications, that they quite often need a very fast access to the input-output, so they have some special mechanism for a faster access of those input-output pins. Anyway, so this is what we know, and we can divide and classify the peripherals, for example, by behavior. So we can say that some of them are used only as the input. When you have, for example, in the ancient time, tape reader, then it was purely input device because you have pull inside the tape and computer reads the punch on that tape and so on. On the other hand, if you have a punch device which writes the data to the tape, then it was output only. As for today, typical even input devices, you usually have even the output for them. And for the input devices like a sensor, you usually again have some mechanism to control the state of that sensor and set up some ranges and so on. So it is typical that we have both. Today, for example, if you have keyboard, then even the keyboard, even that it is considered as input device, it has indication LEDs and other stuff. So basically, it is input-output. You can test what is the connected and so on. So it is input-output device. Then we can divide the peripherals by connection. So there can be a direct connection between the peripheral and processor, or it can be indirect connection through some bridges, some communication controllers, so for example over the USB and so on. The partner to the computer can be, and the peripheral can be the human, so it is human input-output devices, or it can be another computer, in the case if you want to interconnect the computers by the network and so on, and it can be even some physical environment, when you use sensors, robots, actuators, and so on. And we can divide those different peripherals even by the capacity or bandwidth of the link. So it is basically a maximum data transfer rate or capabilities. Sometimes it is not so critical to be able to transfer a large amount of the data, but if you want, for example, to steer the car on the road, then it is more important latency of the communication. So those are those typical and important parameters. If we look at the example of some human-machine interfaces and peripherals, then you know the keyboard. It is considered as the input device, but it has the output to control the LED, to set the repeat rate, and so on. So it is, in the fact, input-output device, and the latencies are not critical. Something like, 5 or 10 keystrokes per second are acceptable, except if you play games when you want probably to have fast reaction on the computer side. If we start to speak about the speaker microphone, which I have at this moment connected, then you need a little higher transfer speed and bandwidth. And if you want to communicate with other person, to use it for telephony or some online chat, then even the latency is critical, because if you have transfer delay of half second or more, then if other party doesn't know if you have finished your talk and starts to speak and you are out of the scenes. Other problem is if you hear the echo, because person hears echo of his her own voice, then if there is a specific delay, then you are totally lost. It is the way how you can totally destroy the speaker, basically. So you need to train for this to survive if there is echo. Okay, then we can have printer scanner interfaces and connection and devices. Their latency doesn't matter so much. But on the other hand, sometimes the amount of data which are sent are quite large, so you want to get the printout in some reasonable time. If we speak about the voice and audio and music and so on, then the typical sample rate today is something like 41 dot something kilohertz. If you multiply that, you want to have the at least 16 bits per channel multiplied by 2 channels, so it is 4 bytes at 40 kilohertz. Then you need something like 160 kilobytes per second, and this is if you multiply it by 8, then you get to something like some megabits per second. And if it should be high quality audio, then you need to go up with the bandwidth. High quality recorders work with 196 kilohertz typically for the audio recording. Okay, if you want to communicate between devices, then a historical solution was a modem. which today, if you have serial port and modems, then usually the basic bitrate on PC computers is 115.2 kilobits per second, but original modems was at something like 200 bits per second and so on. And sometimes you are in this situation today as well. My colleague has a similar kit or hardware which we use there for our semestral works and semestral project on the orbit, and they have communication speed of I think 200 bytes per second, no, 200 bits per second, and only for 20 minutes when it is over the area which is of interest. So even today you have sometimes troubles that you need to communicate with quite slow link. Okay, if you go to LTE and 5G and so on, then the maximum bandwidth of the communication is much, much higher. If we go to the standard wire networks, then Ethernet started by 10 megabits per second, then 100, now it is usually 1 gigabit, but there are optical connections up to terabits per second. By the way, the speed up of communication is probably today most fast growing parameter in the computer science and area, because the capacity of the disk goes up, but not so fast. Speed of memory, it is much, much slower, as we have seen, and we need to resolve it through the caches and so on. But for the communication, the growth is really rapid and exponential still. And speed of single core is limited already by the physical means, so mostly. So, okay. We can have even data storage devices like our hard disk and solid state drive, some magnetotape units. Communication speed is according to the connection. Usually you can have a fastest SSDs which needs to be connected directly to the main peripheral bus, not to some SATA or another means to be fast. For some tapes units and so on, which are still in use because their capacity is very, very, very high, are sequential only, so you need to order the operations. If we speak about the external sensors and actuators, then for example, if you have a laser finder, rangefinder, which allows to obtain a depth image of the surrounding, which is, for example, good peripheral for autonomous driving and so on, then you can start with some USB, where original USB 1.0 was 12 megabits per second. Now we have the USB version 2, which has 480. USB 3 can go up to 5 gigabits per second. We have those communication networks, and even some rangefinders today are connected by this 10 gigabit Ethernet network to deliver the amount of data which are necessary to the computer. It is my colleagues from computer science department has such rangefinders and processed them directly in the FPGAs. If we speak about the actuators, then usually the transfer speed is not so important, but if you want to have a close loop control, then latency starts to be very important. And if we speak about DC motors and their control, then some latency, little below 1 millisecond, is again to control the robot. But if you want to do the full field-oriented control of permanent magnet synchronous motors and such stuff, which we do, then you need to go to something like 4 or 8 kilohertz and even faster. We have a commutation coprocessor which runs at 20 kilohertz for those kind of applications. Okay, so it is some introduction. Now we return back what we already have. So we have our processor, where we have some data path and some control path, and we have those memories, and we have decided we take those memories out and left the ports on the chip, which allows to communicate with external world. And those interfaces, usually for the simple parallel bus, consist of some set of the signals. So for example, for a 32-bit computer, we can have typically connected peripherals in 32-bit address space. There are some problems that usually we have even 32-bit or 16-bit data bus, so least significant bits of the address bus, 0 and 1, for example, are not used directly, but we can skip that. So in this case, we use that address to the address space where we have data and some another peripherals as a 32-bit number on the 32 address wires, and then we have there a data bus which has some weight. Sometimes the blocks of 8 bits are controlled by individual byte-enabled signals. So if you write, you can decide that you write only into the specified byte at specified address, not onto the whole word only. But in this case, if the data bus is wider than the 8 bits, you need to have such byte-enabled signals. Sometimes there are some control signals as well, and some another control signals for handshaking between the peripheral and processor and so on. So, as we have spoken about those mechanisms, how we can access the peripherals, and the historical von Neumann concept was that there are specific instructions for the input and output. So on the x86 Intel processors, you can find those specific instructions which are used for the access of the peripherals, which are mapped to relatively small address space of 64 case registers. But on the modern RISC processors, usually the peripherals are directly mapped into the full memory address space. And even on x86, when you want to have, for example, a video accelerator, graphic card, and so on, then you usually want to access the whole address range of whole display. It doesn't fit into the I/O space, so those peripherals are mapped into the memory space, and you can access them by the same instruction which you use to access the memory. And it is even on those chips which has the special input-output instruction, usually today practice is to switch to the memory-mapped peripherals, which is the second option, and on the RISC-V and most of the RISC processors only the option. And even many complex instruction set computers has only the memory-mapped peripherals. The mapping of the peripherals to the memory address space is usually today a runtime, at least partially or fully configurable, because in the past time, when you have a new card, you have to study what is the allocation of address space, physical address space of the given computer, and then you need to jumper on the board into which address it should be mapped in the physical address space of the computer. Today, you do not want to take care about it, and mapping, for example, a video accelerator would be very complex because it has many ranges which are necessary to map with different properties into the address space. So it is done more smart way by the base address registers and so on. Okay, If we start with very simple peripheral which is connected to our RISC-V processor model, then there are no special instructions to access the peripherals. We use the same load word, store word, or load byte, load half word, and so on instruction as for the memory access. And we divide the address space, that unified address space, to the part which is used for the memory. And usually you have enough space there that there is a lot of free space because you have, for example, 1 gigabyte of memory, 4 gigabyte address space. So into some part of the rest, you can map the peripherals. In the case of our simulator, the address where our start to map peripherals is, I think, 0FE. Okay, we can look at it. It is specified later here. And how it is done? If you have a classical processor with external data bus, then usually it has one set of the wires of the signals to output data and read data back. So they are three-state and change the direction. On the other hand, if you design something on the chip, then on the chip today practices that there are no three-state buses. So basically you have a separate signal to write data and separate set of the return of the read data back to the processor. So it is in line with what we have seen in our design of the processor. So we have there some signals to write the data. Then we have there some signals which we have seen in our processor to specify the address. And we need to select if the given address falls into the memory range or if it is matching the input-output range. And for this, we add there the device which is called address decoder, which reads a part of the address signals and specifies and combines. If there is a write from the processor, then the data can be connected to both peripherals and memory. But a write signal, when it arrives, is gated by the selected address. So in the fact, if it falls into the memory address range, then the write signal is delivered to the memory, and memory stores the data. If the address falls to, for example, this input-output peripheral or register, then the write is activated or enabled only to this register which strobes, captures data from the data signals. As for the reading, then for the reading, we take the address, again use address decoder, and then we can decide and gate, for example, even the read memory or read peripheral signals, if they are here. But if the bus is not three-state, then the critical at the end is a multiplexor which selects according to the address specified by the processor if the data to the processor should be delivered from memory or from some peripheral. This example. As for the address decoder, there can be a central address decoder which has individual wires, so-called chip select or device select, which select individual peripherals on the board. Or there can be a distributed version with peripherals which has their own base address registers and distributed address decoder. And at the moment when the processor writes to the address which matches the range, which is covered, which is mapped to given device, Then the device responds, okay, I am here, and starts to communicate and accept data from the processor. You have often this fast bus connects only the core components, and then if you need to add more components, then there is a limited fan out on the signals on the bus. So usually you add the bridge, which can hide, again, same type of the bus below, or it can be some another kind, slower bus for cheaper and not so fast peripherals and so on. For example, on the PC, you go this way down to the bus which has 4 data bits, and this is used to connect the BIOS flash, and I think that even the keyboard is still connected by this 4-link line at the lower part. So, and then the actual keyboard is connected through the synchronous serial communication. And again, even if you have those multiple levels, this hierarchy of buses, then each level can have its own address decoder, or it can have, again, such mechanism how to allocate and set up the addresses to the peripherals. Okay. And if we want to exchange data with the peripheral, then it is quite often that the peripheral doesn't have data ready at a given instant of time. For example, if you want to read a keyboard, then typically you find that there is no new key. Or if you want to send the data to the serial port, then typically there are sent still the previous data byte, and you need to wait. So CPU needs to check if it can write a data to the peripheral, or if there are available data to read from the peripheral, new data ready to be read. And one possibility is to provide in the peripheral the access to some status register, and processor periodically pulls if the state of the peripheral has changed, and if it signals, okay, there are new keystrokes or new data byte or new packet, for example, from the link, then you can move the data from peripheral to the memory or vice versa. But this has a big disadvantage, that processor wastes the time to pull the peripheral, and in the modern system, during this time, the processor can switch to some another useful work. For example, in the time when there is no keystroke, it can enhance the resolution of the game image on the screen and so on. So basically, usually you do not want to burn the processor time on this periodic pooling. So in this case, you can extend the peripheral with the ability to signal the asynchronous events. It is called the interrupt or interrupt-driven communication, where the processor is informed. Basically, it does something else. For example, will enhance the resolution of the game output, and you press the key, and at that moment, a keyboard controller sends this event. This results in the switch in the processor to the interrupt service routine or interrupt handler, and it can process that operation, and the actual task which processes the input can be stopped by operating system, and when the new data arrives, it starts the task again and release it to continue and process the data and prepare a new state to display on the screen and so on. Okay, so we have there this possibility to work with interrupt-driven solution, but at the moment when you have, for example, sustained data rate of the packets coming from the network, then in such case you usually do not want to spend time on each packet, each byte, to move it from the card to the memory. And even, for example, with the disk, if you want to read a whole packet or whole sectors or cluster or some set of the data, you basically know that you want to have those data in the memory. Maybe you will need to process them by the processor later, but sometimes you only need them to get to the memory to send them, for example, as the web server to the network. So you do not want to waste time to take care about each byte of those data by the processor. And in this case, we use a mechanism which is called direct memory access, which allows to instruct the peripheral where data should be stored into the main memory, and peripheral only signals if the whole new packet or set of packets is delivered to the memory. And in the fact today, even that rate of the interrupts which would came from the adding individual packets into the memory would be so high. So for example, Linux only waits for the first interrupt from the arrival of the packet, and then it switch notification by interrupt off, and only looks for the data in pool mode, because it is faster, because there is no necessity to do the complete interrupt processing. And only at the moment when there are no new data from the network card, then in this case, it switches back to the state where it starts to take care about something else, and left the interrupt-driven notification to inform it that a new packet has arrived. And then this switch of the mode to the pool API is done as well. Okay, so same for the output, so it is a typical way. We will look at the interrupt-driven communication during the lecture 9. For the full direct memory accesses, we only look at it in very quick way, because it starts to be a little more complex. Anyway, if you look, for example, to the Linux kernel, how it accesses the peripherals, then it is very much simplified diagram. But what we can see here, that there is some interface to the user space. That interface allows to communicate with some subsystems, like, for example, file systems or the pseudo file system, which represents some hierarchy, or with some devices on the logical level. And then there are low-level drivers, which, for example, maps individual requests from the file system for individual blocks on the hard disk to the SCSI layer, which then provides a communication which actual, for example, ATA or ATA communication disk, so it would be something like this. So basically, you open the file, try to read the file data through the read-write operation, and it activates operating system and goes down to the file system and so on. If you want to access the serial ports and some real peripherals, then even on the Unix system, you can find abstraction of those devices in the dev pseudo file system. And for example, TTY is the actual console which allows you to write data. It was in the past a serial, but today it is virtual. But anyway, if you, for example, try a dev and TTYS1, then if you have a serial port, then you can open it, and then you can directly access through this. Basically, you skip this one, so you go directly here to some level of the serial ports down. Okay, so There is even option to access the hardware directly, which is what we will use during our semestral work, semestral project, because if there is something mapped to the physical address space, then even that you are running in the virtual address space with your application, if you have a proper rights, you can remap part of the physical address space directly to your virtual address space and then use instruction to access a memory range, which in the fact will access the actual peripheral. Okay, the standard way how you communicate with the peripherals and files and so on the Unix system is through system calls. We get to this during the lecture number 10. So only very quick overview here. Basically, you want to invoke those services of operating system, and you can use standard C functions, which are wrappers for the given architecture specific system call interface, which you can ask the kernel for the services. So if you call the open function, then it is a function in the C library, and it is converted to the system call into the kernel, which finds which peripheral or which file or file system serves a given file, okay, in this case, the file is in the fact a hierarchical name in some namespace only, and provides you a handle, which allows you then continue with, for example, read, write, close functions, or input-output control functions. And if you call the read, then if you open the device in the blocking mode operation, then the typical rule is that if there are no data available on the given peripheral, link, network interface, stream, communication stream, that you block, but you do not block till the whole required length is available, but only till the first byte, at least one byte is available, and then the return, then the read function returns, and it provides you information how many bytes has been delivered to your buffer, or bytes characters. Sometimes it works on the packet granularity. So, for example, if you read from the socket, which is listening for the UDP communication, then you can be sure that each read operation returns a whole packet. But on the TCP, you wait even for the first byte because it is the string communication. And if there are no data, then the operating system blocks the task, suspends it, switch to some another task, and when data are again available, then through the interrupt and some synchronization mechanisms, it again releases the task to run when data are available. There is another option that you can open the device or socket in the so-called non-blocking operation mode, and in such case, if you try to read the data and there are no data available on the kernel side, then the call returns -1 and reports the error. Okay, it should be only 2 errors here. It returns E again, or E would block, and you know that you need to repeat the operation again. If you do it in the busy loop, then you are again on that wasting the processor time. So you probably should set up some mechanism which informs you when the device becomes ready by pull or select system calls and so on. And then the operating system receives data into some internal buffer, and when they are ready, your task is again notified through those mechanisms which you can use. Okay, so there is a question because you have used scanf function probably during your second homework. So what happens if you try to read formatted input, for example, those integers, and you call the scanf, and the data are not yet available? So what happens? What do you think that happens in such case? For example, if you send your image by pipe to your application or something like that. No. It would be if you open it with open system call and in non-blocking mode. But if you open it with fopen, then it is opened by default in the blocking mode. So it means that it waits at least for the first byte, but first byte is not enough to fill all the, for example, if you ask for 3 integer values, then from the first byte you do not know, because it can be the part of the first number or it can continue and so on. Okay, so C, yes, in this case, and it can be suspend, get some data, and again it can be not enough to fill everything. So the fscanf function will wait for the data. Operating system below will suspend the task at the moment when there are no data available. But even if there is single byte, then it is wake up, it reads the data, finds that it has no new line character at the end or something like that, or space, which it is waiting for. So it again tries to call the operating system read system call, and then when the whole line or all the required fields are filled, then it returns. If there is an error in the communication, only if there is an error returned by the communication, then it returns prematurely with the information that, for example, only the first 2 required fields has been resolved. So now we look what we can test on our Qt-RV Sim simulator. So the first set of the peripherals which are interesting to test are rotary knobs. Those are 3 knobs which allows to tune the value from 0 to 255. And this way we can tune the 1, 2nd, and 3rd byte, and the read from that address will return the actual state of those 3 knobs. And if we have the RGB LED with same mapping of the color components, which we have 2 of them on our simulator, then if you read this value and by single load word operation, and in the next step you store it to the RGB LED, the output register, then the LED changes the color according to your tuned value. Then you can read 3 push buttons. So basically, when you press the knob, then this bit is set to 1. If you left it off at the idle state, then there is a 0. And this one, no, it is not full byte. That it is 5 bits. Those 5 bits are not used in our case. And this way you can check that you can read something from the peripheral and write something back to the peripheral. In the fact, you will find this panel with the peripheral. So those are those 3 knobs. Those are implemented this way because they are equivalent to our education kit, physical kits, where you have those 3 knobs. We have think about adding the touch screen to our design, but then we decide that if it should survive some years, when at the end some lower number of thousands of students has worked with the kids, then the touch screen would probably not survive for long. So for this reason, we decide that the knobs are interesting input device, and it is used, for example, on the measurement instruments, oscilloscopes, and so on. So it is relatively interesting peripheral. So we have added it to our boards, and it is here. And the value of the knob is read from the register, which is here at this offset 2,4 in the range of the registers. So basically, usually because you can have multiple instances of peripherals and so on, and you want to do the mapping of the peripheral only once and so on, you use some base address for a given peripheral, and then you work with the offsets. But you can add those directly, and then you get even directly this address. And because we do not have a memory management unit emulated by our simulator, then you can directly access this address and read the value which is tuned on the knob. And then there is a control register for the first LED and second LED. So you can write them back. There is even some debug register where you can write a 32-bit word, and it is displayed on our kits on individual LEDs. So you have there the red line, LED line with 32-bit LEDs, 32 LEDs, where you can lit on and off each individually by the bit. In the case of simulator, we even show the value in hexadecimal or in the decimal. So you can use, for example, the values on 2 knobs as the input to your calculator, sum them together, and return them back, and you will see the binary hexadecimal and decimal value. So you can do something such simple with it. Okay, there is an example. So you can use this pseudo instruction which use load upper immediate and add the I to combine together the full 32-bit address representing the base. Then we set the another register to -1 in this case, for example, this way. And then what we can do is that we can use the offset of our knob register, combine it together with the base, which is stored in the A0, and use standard load word operation to get the value to the T0 register. Then we can take this value and store it only on the different offset in the same peripheral, and we have our first application which allows to set the color on the LED. And we can sort the value with this -1, which are in the fact all Fs. So if we sort the value, then it is in the fact computing of the first complement. So we compute the complement color in the components to this color and can set it to the another LED. And we can even use some shift, for example, here, and to modify something, and so we read there the bit, we shift to the right this register where on the position 24 is the red button pressed indication. So if we press a red button, then when the execution gets there, then we find that the given bit is set, and RGB is in the fact 24 plus it is Yes, it is this set, and it is 26, because we tested against the bit number 2. And if it is set, then we know that the red button has been pressed, and we finish the program with the e-brake operation. Okay, so there is a question. If we want to obtain the green value from the LED, we read it, from the LED, from the knobs. Then we have there the RGB components, RGB. It is 0 to 7, 8 to 15, 16 to 23. So which of those operations returns the green component on the green knob if we tune it? It should be a B, because we need to shift it to the right by 8 and then to mask it by the 8-bit mask. And we have the value which is on the knob. Okay, now we look on the asynchronous and synchronous buses. If we have some asynchronous type of the communication, then it can have two variants. One variant is that there is synchronization for each individual bit. This is usually not used. So much more used asynchronous kind of communication is that there can be idle state, and then when the character or byte is sent, then there is some start bit which allows to recognize that there is now the start of the character which we can or should receive. Then we know that the individual bits are set at some so-called baud rate, so some pace in the time. So from that start bit, we know that if we know the speed at which the bit has been sent, that if we wait even the time of 1/2 of the bit later, then we can strobe the value which represents the first bit and the next bit and so on. And if we want to be able to resynchronize to the data, then it is necessary to insert between the consecutive sequence of the bytes at least one bit stop bit where there is a 1, and then again transition to the 0, which can come immediately or later when the next byte is available, informs that there is start of the following byte. So it is asynchronous, typical asynchronous communication. It is more complex because usually we have some combination of synchronous and asynchronous, because serial port is asynchronous on byte level, USB on the level of individual USB packets. On the SATA it is on the individual sectors and so on. Then we can have synchronous bus. The simplest way how to synchronize transmitter and receiver is to provide a separate clock signals which informs the receiving side when the bit, individual bit or byte or word on the parallel bus is ready to be strobed and is valid and so on. In those synchronous cases, we can synchronize by clock by racing edge or failing edge, or for example on DDR RAMs and so on, we transfer data at the racing and falling edge at both edges. An example of synchronous, or sometimes called pseudo-synchronous, is even the PCI Express, because there are some possibilities how to delay the communication. Okay, now if we go to the asynchronous serial communication, then the serial link or serial port is used. I have found that the first variant of this communication has been used in 1930 or even earlier. So at that time, only the 5-bit characters has been sent, or even shorter, but it is really very old method of digital communication. And initially it has been used over some modem communication on the switch on the dedicated wires, or then later on the switch telecommunication network, and even later on some more modern systems. But even that it is so old that it is still used for the initial debugging and development of almost each system. So, for example, on most of hard drives, you find somewhere the pins or the pads on which you can connect and communicate with the firmware of the device. In each of your mobile phone, there is internally this communication which has been used for the initial debugging of the system on chip and so on usually. So basically it is still quite common, but not so much seen on the PC boxes or external connectors from the mobile phone and so on. And it doesn't provide a dedicated clock signal, because we know that we find the start of the character by this transition from 1 to 0. Idle level is 1 for some reason, and it is represented by some, because it is negated on the link, so it is represented by negative value, but we can skip that at this moment. And in this case, both sides of the communication needs to know the speed which is selected for the communication, because it defines a length of individual bit. And at the moment when we have there the start bit detected, then we need to wait 1.5 bit time to find and strobe the value of the bit 0, then bit 1, 2, and so on. And usually today we use whole 8-bit communication. Sometimes it is extended even by the bit 8. In the fact, it is 9th bit of the communication, which informs if it is control character or address or standard data character. And then we usually use or can use a parity optional, which allows to detect a bit flip in the data, that you know that the character has been somehow noise or something, that it is not correct. And the speed which is used at the start, it was that something like 200 bits per second and so on. Today it is usually the basic speed is 9600, but most typical default speed is that fastest used by standard PC serial port, which is 115.2 kilobits per second, but you can quite often go even to the faster communication speeds. And there are the standard. This is that original standard to connect the computer with switch communication link modem, which modulates the ones and zeros to some beep signal on the link which has been delivered over the switch telecommunication network. And in this case, this is the standard which was designed to connect only the computer with that single modem, or today two computers together. On the original levels, it used this signaling where 0 is represented from +3 to +15 volts, and a logical one by -3 to -15 volts on that communication link line. It is full duplex, so you can communicate in one direction and another. It has been used, for example, to combine a keyboard terminal with keyboard and some output to the printer or to the screen. So there are two pins, one which is for sending, one which is for receiving, and other side has crossed them. So basically what is my TX pin is receiving pin of the other party. We can use the optional handshake signal to stop the data source to send the data if our input buffer would be overwritten, overflown with too much data sent. So basically it has this handshake. Then there is another standard which is using only the 5 volt levels, only 0 and 5, but it is differential. So basically the one is sent as a Rx plus at plus 5 volts, Rx minus at 0 volts, and it is for the this is for the 1, and for the 0 it is vice versa. So in this case it has big advantage that if there is a common mode interference from some noise and so on, then even if both signals are shifted with the voltage shift, then you still can detect if the 1 or 0 has been at the start. And in this case, again, we have this one pair to send data, one pair to receive data, and thanks to this differential signaling, it can work on relatively long distances. And this is full duplex, but usually it works such a way that we have one central device which connects the Rx and Tx link to the multiple devices which cannot communicate each with other, because Tx, this is Tx, this is Rx, this is Rx, and this Tx goes to the Rx of the central node. And for sure the Tx from the devices has to be switched to the idle state when the given device is not selected. But it has a single node which can communicate with all others, and other can communicate only with that single node. There is another variant which is called RS485, and in this case we have only the single link, again differential with 2 wires, which is connected to all devices, and all devices can communicate through this link and with each other. On the other hand, in this case, it is necessary to ensure that at given instant of time, only the single device starts to communicate, because in another case, there is a collision. So there can be some mechanism how to allocate the bus to the individual devices, for example, by passing some token or by some rules at which time which device can communicate and so on. So this is the option for those kind of the communication. And on our simulator or even on the devices, usually find the device which is called a universal asynchronous receiver transmitter. And in our case of the QTRV SIM, it is represented to the processor side by 4 registers. The first register is receiver status, and if you check the value of the bit 0 in this receive status register, which is somewhere here, then if the bit 0 is at 1, you know that if you read the value from the Rx data register, then you get the actual byte which has been delivered from the terminal, from the user, for example. And the mechanism here is such a way that at the moment when you read the value from the register, then it is removed from first in, first out queue, which is on the input to the peripheral. And if the queue becomes empty, then it automatically clears the bits that data are ready. And you can use that pooling mechanism to access this peripheral and to read data which are written to the input field of the peripherals in the simulator. So it is classical solution. There is possibility even to emulate that interrupt-driven communication, but we left it for some another lecture and seminars and so on. Then we have there transmission status register, and this bit indicates by bit 0 that the transmitter has finished sending of previous data and it is ready to receive the data to be sent next from the processor. So we can look how such code looks in the how to write a character or string to the terminal and so on. So again, we have there some base address of our serial port. Then we have there the offset 0, where is that ready mask, that bit 0 mask, which allows to check if the data are ready. Then there is a bit number 1, which is used for the interrupt-driven communication. Then the data register for the receiver is simple register, 32-bit, but only the 8 least significant bits are filled by the data. So it is at the offset 4. At the offset 8, we have a status register for the transmitter. And again, there is a mask of the bit 0, which informs that we can store that it is ready for the next byte to be sent. And then the mask to enable interrupts. Again, we left it for the later. And there is the actual data register. If we write the data to this register, they appear on the terminal. And if we want to write a famous hello world on our terminal, then we set up the A0 register to point to the base address of the serial port, A1 to point to our text which we want to write, and that text is in the data section, and its address is assigned to the label text1, and because it is not ASCII but ASCII Z, then the terminal 0 character is added after the string. So it is null terminated, same as in the C. And okay, so we have done all necessary setup. Now we load the byte. So it is same instruction like load the word, but this loads individual byte from the address. So it takes the age here. We check if that is the final 0 character. If it is not 0 character, then we move the pointer to the E from age by this addition. Then we load word from the status register because we have the base of the serial port set to A0. We check if it is ready to accept a new character. If it is not, then we loop there in the busy wait till there is a available buffer to send the data. And the actual sending of the data is done by writing this T1 to the address of the TX data register. And then we continue with the next character. So it is a simple. And at the end, when we read that 0, final 0, then we know that we are at end character and we finish by E-break. For the reading, again, we can set up address of the serial port. Then we can define where is the start of some buffer where we want to store the data. And for such input, it is quite good to consider that we can have some evil user who will write a longer line than is the capacity of the buffer. So be careful, see getS function doesn't take care about this. So it is, you should never use getS function. It is dangerous. You should use fgetS or some another getDelim and so on, which ensures that the data cannot overwrite after the end of the buffer. But we know that we have reserve 40 bytes, decadic in this case. Now we read the status from the receiver. We check by the masking other bits out if the register ready, Rx status register ready bit is set. If it is not, then we wait for the ready condition. If it is ready, then we load the actual data and store the data to the buffer. Then we check if it is the character with decadic value -13, which is \n or new line character. If it is, then we end the procedure that we know that we have our line read. In another case, we try to add the we add one to the pointer to point to the next location in our receive buffer, and subtract one from T2, which is our capacity, remaining capacity in the buffer. And in the case that we still have not filled the whole buffer, then we can continue. In another case, we can accept this line as the full line and process it, or we can signal the error that the input buffer has been overflown, that too much data has been written. And you can click here on the terminal in the simulator and see there a hello world. I will show it during the seminar, not now because I have spent too much time to set up the recording. And it works exactly the same even in the pipeline version, because for our processor, so-called commit stage is a memory stage. So when the instruction gets into the memory stage and it is not a mask there as some incorrect one, then it is, there is no difference if it writes to the memory or if it writes to the terminal. So even for pipeline version of processor, it works exactly the same as for non-pipeline version. Only you need to wait till the store word instruction, which is here, gets to the memory phase, and at that moment, the character appears on the terminal. So relatively easy. Okay, so if we go to the summary of peripherals access up to this point, then we have seen that this method which we use on the QTR vSIM in this example was busy waiting. Program constantly asks if something has changed, and it is inefficient because a CPU cannot use its time for something else. Instead, it wastes the time to ask again and again to the peripheral. So we will introduce the option how to implement this with interrupts on the CPU. It is a little more complex. And in such case, we can have some another process or some another task which can do something else useful for during that time we work with, we wait for the data from the peripheral. And we know that the data has arrived from the incoming interrupt, which notifies the processor and start the handler function, which can check peripheral state and process it. The data can be stored into some buffer, for example, and then they can be delivered to the application when whole line is ready and so on. And it is the area which is teach here during the operating system course. Now we look onto the interconnect buses which are used in the personal computers, so in the PCs which you use. The original design from IBM has used the so-called industrial standard architecture ISA bus, which has been never standardized, I think. It was such standard and not standard, but because they open the design, it allows to connect and develop the add-on boards to other companies, which was a big advantage of the PC architecture, that it allows to connect the another devices and so on. But it has disadvantages that it was quite slow, and there was that problem that you need to switch on each add-on card at which address it should be mapped and which interrupt it should use. It was not so easy. Then came the PCI bus, which was parallel 32-bit or 64-bit wide. It provides a burst mode, so basically only a single cycle for addressing, and then we can continue. It has even the extended versions which can go to 530 megabytes per second. It has a big advantage that it has a topological enumeration. So basically you can ask what is connected to which slot in the main board. And this allows plug and play support, where you detect which cards are there, how big address ranges each of them needs in the memory region. And you can set up the base address registers in the cards to recognize where they has been mapped by the BIOS or operating system. And it allows to map to the I/O space to support that original Intel in and out instruction, as well to the memory address space. It even allows to the peripherals to initiate the communication back to access directly the memory and store the packet to the memory without the CPU. CPU setups the peripheral where the data should be stored, but doesn't need to assist individual bytes. But even that communication was too slow for the fast graphical accelerators, so there has been defined a dedicated bus based on the PCI, which allows to connect high throughput graphic accelerators and sometimes even network controllers. But then the industry has switched to PCI Express, which is from the logical point compatible with PCI and with operating system drivers and so on, but the actual physical implementation is the serial link, which is very interesting. Okay, if we go to the PCI, then it is the shared bus, where we share the data lines and address between all the peripherals on the given level of the bus. Then we can have there the bridge, which gets us to the another bus with shared signals. On the other hand, the PCI Express and USB is switch topology where actual links are only point-to-point. And if we want to communicate with some peripheral, then we need to, or the switches according to the address which we want to write or read, routes the packet to the correct link. But anyway, you achieve this routing only by those load word, store word instruction, and it processing is mapped to the packet, sent to one direction, sent back. It has a disadvantage that it takes some time. So it is interesting then on the modern PCs, if you want to implement a closed loop control for some motors and so on, that you are getting at the latencies and speed which was typical for the PC in 1980. So it is interesting that for the latencies it is not good. You have great throughput. If you need to deliver the data to USB or video here, for example, through the USB and PCI Express to the hard disk through the PCI Express mapped SATA controller and then to the disk and so on, it is great. But if you want to have a fast control with low latency, it is quite interesting how it is problematic even on those modern devices, and it is much easier even on small MCUs, which are much tightly coupled to the peripherals and so on. Okay, if you look at the original PCs, or not original, but at the PCs at 1990, because original PC was something 1980, but if we look at that, okay, middle age from your perspective, then we have there the processor. It has been connected to so-called NOR bridge. The name NOR is for that reason, that bridge, it is connection of the processor to something else. So this is a bridge, which bridges the buses. And NOR, because on the plan of the mainboards, it was usually written on the top part, so basically on the north on the map. And it connected, it includes the memory controller, then you have there the memory channels for the DDR memories, then AGP port to the fast graphic card, then some, at that time, PCI Express or local bus or some special link to the South Bridge, which implements some peripherals directly in the South Bridge. So for example, USB usually divide there the communication and control the PCI slots for the add-on cards, and using this 4-bit communication for those slow peripherals connected to LPC, low pin count bus, has usually some controllers to connect the hard disk and so on. So it was the old setup. Today, if we skip the development to Ryzen or contemporary Intel systems, then the memory controllers are integrated directly on the processor chip or in the processor socket, because maybe you know that the AMD is not a monolithic chip, but it is the set of chiplets with individual groups, about 8 cores, which are then soldered on the interposer on the some connection where low integration I/O chips and other stuff is in the single package which you connect to the socket. And there is directly the memory controller, usually for multiple channels. Then there are PCI Express controllers and the communication to connect graphic card and some other devices. And even the USB and some stuff is sometimes directly on that system on chip, which is a PC processor. And then we have there a chipset, which is something which has remained from the South Bridge, which connects the PCI Express, USB, communication devices, hard disk. Usually today hard disks are already connected to the PCI Express NVMe, the solid state disks. And you can have there even, for example, board monitoring controller, a management chip which allows to monitor the server from the LAN. So this is the options what can be there. And if we look now a little back to the PCI, so PCI is not important today for the other interconnection bus in the PCs. But internally inside the chip, those mechanisms which I describe here on PCI bus are still often used. And because the PCI bus is older bus, it is still relatively simple to describe it. So we start with that PCI bus, and the mechanism even on the PCI Express is compatible with the PCI. So what is the PCI peripheral component interconnect bus? It is a synchronous or pseudo-synchronous bus, which where all the data transfers and state change is controlled by the racing edge of the clock signal. When some processor or some device wants to initiate the communication, then it needs to request the bus control signal, so it gets the information from the bus arbiter that it has now time to start to communicate, and we will look at it a little later. And for historical reasons, most of the control signals are negated. So I will say that when the signal is active, it is so-called asserted, but this is typically low level or level 0. On the other hand, when the given signal is not active, it is de-asserted, and typically it is sent as the value 1, or the logical level basically is vice versa to the actual link level. So in this case, 0 here is marked that 1 is inactive, and this 1 here is that it is active at this instant of the time. And if the actual topology of the PCI, because it is a bus which connects multiple slots, so we have there those slots which are connected all with matching pins to the address data bus, which is shared, so we use same signals to send data and address. Then there is some control and bus enable signals and some another control signals, but there is one specific thing, that each slot has the individual signal which is called the ID cell, and this specific signal is used at the start that you can notify a board add-on card in the given slot, okay, I want to read your identification. So this is way how the PC enumerates at the start the inserted add-on cards, that it reads the identification with this active ID cell signal. Address data bits are 32-bit for the PCI X, which is extended version. It was even 64-bit wide. There are those 4 signals for the 32-bit version, which informs if the at the start what is the kind of the operation, if it is read, memory write, I/O read, I/O write, interrupt acknowledge, and so on. And then during the data words transfer, it informs which bytes are active and which are out of addressed instruction and so on. So basically, if you use a load word or store word, then only a specific single of those 4 signals corresponding to the given byte in the word would be activated. From the control signal, we start with the frame signal, and the actual transfer, the transaction for the write operation starts such a way that, for example, processor, which became the initiator of the transaction, decides that it wants to write the data. It needs to ask a bus arbiter if it can control the link. At the moment when it can control the link, then it asserts frame signal. This asserts means that it goes to the low level, but logical meaning is that it is active. And it provides on the command wires, it provides information that it should be a write transaction, and it set up the address. And at the racing edge here, all the peripherals which are connected to the bus compare the address to their base address registers, and if the address matches, then in this case, a given peripheral informs by this device selected signal that there is somebody who will receive data. And in the next clock cycle, there are prepared data which can be accepted by the peripheral according to the byte-enabled signals and so on. And if the frame signal is still active at this moment, it means that there will be a following data sent in the next clock cycle. So at the moment when we want to send the last data, we deassert the frame signal, and this is information then in this clock cycle the last data would be sent. But sometimes the actual data are not accepted by the peripheral, so the last data transfer or some data transfer can be prolonged to the next clock cycle. We will see it a little later. So basically, if the device responds, okay, I am selected, initiator, so it is that one who sends the data in this case, or who controls the bus, address the peripheral, says, okay, initiator is ready, and the target informs, okay, I am ready for the transaction for the data. Then on the next racing edge, where all those signals are strobe, the data are transferred and considered to be delivered to the device. Then, for example, there is that we want to send the final data, but in this case, the target, the device, needs, for example, to process data, to store them to the display or to do something with those data. Then the peripheral, the target, informs, okay, I do not accept the data in this clock cycle. So this clock cycle, there is no transfer of the data. And only when, again, the peripheral or target becomes ready for the data, then if both the initiator and target are ready, in this case, this clock cycle informs that the data are transferred. And this way, the actual transfer has finished, because this was the last data transfer for the given transaction, and now the bus becomes free. So it is that last transaction, and at this moment when the device samples the frame signal at 1 during the state where both sides has been ready, then it knows that it is the last word transfer. It deasserts the def cell, and even the rest of the signals are left in the inactive state. And this is the release bus, so basically this is what I have already said. But you have all in the slides. For the read transaction, there is a small problem that we send the address on the AD wires and these signals, and now the device recognizes that it is a read operation, that address matches a given device, but we need to allow some time when the actual initiator of the transfer disconnects from the bus, and the target device, after this racing clock edge, connects to the bus. So for this reason, the device didn't inform that it is ready for the data directly. It delays by this information that target is not ready, that during this clock cycle, no data can be transferred. And it is the rule, so basically it is not possible to transfer the data in the read transaction directly following, in the cycle directly following the address. And now the rest becomes exactly the same. In this case, we do not have there any delay because both initiator and the target, the device sending data in this case, is ready for whole time. So when we sample that the frame signal became 1, then it finished. If only a single word should be read, then the frame is asserted only during the address, and it deasserts there because only that single data transfer will occur. Okay, what are the disadvantages of the classical parallel PCI bus? The one disadvantage is that it is half duplex, and so data cannot be sent in both directions at the same time. And if, for example, you want to deliver a data from the network to the memory and some other data from the processor to the display and so on, then when the bus is blocked by the transaction, no other can use it at a given time. It is short time, but basically the bandwidth is divided to the communication devices. Multiple devices share the bus. It can, slower peripherals can even by their delays and waits slow down the faster peripherals. Only a 33 megahertz or in the another variant 66 megahertz can be used. If you have a 64-bit variant, then that PCI X allows to extend up to 133 megahertz. But it is quite a big problem. There was even variant for 533, but it is almost impossible to route this correctly on the board. So this is the limiting. So basically, this is limit something like 1 megabyte per second on the bus, which for the 10 gigabit network or fast displays or cameras became the problem. And the connector, even for 32-bit version, needs 62 pins and 124 pins for the 64-bit versions. For the pins yes. And so basically, it is a problem. The main disadvantages of those parallel buses is that if you want to send data in the words one after another at relatively high frequency, then the individual wires on the routed on the board has a little different delays, which is not any problem if you have a low frequency, because you have there the clock signal. It informs, okay, data are ready, and you sample them, strobe them at the receiving side. So it is no problem. But at the moment when you increase the frequency to deliver a lot of data, then you get to the situation where you have basically no way, no instant in the time when you can sample the corresponding color data, because some has gone faster, some from this blue has been slowed down, and if you look at it, then basically it is almost impossible, or from some moment impossible, to find the instant of the time when the given data word bits are on the all wires. So basically you cannot have a very fast parallel links. And it is a big problem. And if you have even the multiple connections to the multiple sockets and so on, it is big problem, and each board would have a different timing and so on. So basically the parallel buses has this problem, and this is the reason why the new standard PCI Express has been designed, and it on the physical level is a peer-to-peer communication, so it is signals are routed only between two devices or device and switch. It is full duplex, so you can communicate in both directions at the same time. For example, send reply to previous read operation and accept new write data and so on. For each direction, there is used a method with differential signals. So basically, it is the same idea which was used on RS485 or 422. It was half duplex or full duplex. And it is using a differential signaling, so each signal is delivered in the pair. It is even interesting that thanks to the encoding, which has a 0 DC level, it is possible to do a separation of the grounds and overcome ground shift by the entering the capacitors, serial capacitors into the signal. So basically there is no DC component delivered. And thanks to this, you can have boards which can float a little according to the power supply, voltage drops on the connectors and so on. On the other hand, you can go down with the signaling, which is below 1 volt and so on. So it allows to lower power consumption and faster data rates. And there is used one signal in one direction and one in another direction in the single lane. We look at it a little later. And it is possible to have multiple such links in the parallel, but they are not synchronized on the bit level. So basically you send the first byte on first link, second byte on second, and so on. And then repeat from the start if you have multiple links. And the delays between links are no problem if the if the delay is not longer than the time to send the whole byte. But there is the flexibility that the difference in the delays up to time to send 1 byte is no problem. And because we need to have the clock here, then the clocks are reconstructed directly from the data signal. And another advantage is that the connector has only 18 pins, active pins, and or 36 signals, from which 18 are ground and power, so it is relatively simple. And in the fact, if you want to route it directly on the board, then it is enough to connect the four pins. The data TX plus minus, RX plus minus, and with those 4 wires you can connect even the peripheral if you do not count the power supply and the rest. So we have done that. It is quite nice if you look at number of the pins and so on. So, but due to the requirement to send data as a differential and allow that separation of the ground through the serial capacitors, we suppress the command mode interference and noise and so on. That's great. But we need the signal which has a 0 DC component. If I say 0 DC, do you know DC component, AC component? You should know that, yes, it is altering voltage is AC. The stereo voltage is called DC. And for this reason, we want to use only such codes which has ideally same number of ones and zeros. And for this reason, 8 bits of data are extended to 10 bits, such way that only some subset of the combinations is used. And how many combinations we can encode by 10 bits if we allow only the same number of ones and zeros. So you have ABCD here. See, okay. So basically, we have 10 options, and we should take five balls from 10, which are numbered, which represent those which will be set to the ones or zeros. It is not important. So it is 10 factorial divided by 5 factorial multiplied by 5 factorial. N over key. You probably should know this from the... So it is not enough to encode whole 256 combinations which we need to deliver the data. And we need even some additional combinations to mark the start of the data and end of the data and synchronization and so on. So what we can do with this? It is a little extended that we use not only those combinations which has 5 ones and 5 zeros, but even the combination which has 6 ones and the complementary which has 6 zeros. And it is interesting that this way we get 672 combinations. But if we take from that second part only 1/2, then we can have those which have 0 difference and those which have positive 1 difference. And then if we use those complementary which have -1 difference between ones and zeros, then we can use such encoding scheme when we send the data with 0, no problem. Now we send the data which offsets the DC component by +1. Then, for example, next by 0, if it came such code. But now if we get another code which would result in new +1, then because we have for each of those codes a complementary code which goes -1, then we select the code which goes -1, and such way we can ensure that in the integral perspective we have never bigger of difference between ones and zeros bigger than a 1, which is quite clever. We have enough codes to denote the starts and so on. So, and it is a patent from the IBM from 50s or 60s, this idea. So it is quite old, but PC has switched to it very late in 2000 or something like that. But it has been implemented even such way that it is possible to decompose it to 2 tables, one which encodes 3 bits by 4, and another which encodes the 5 bits to 6. And there is the example of this table for this first part of this code. So basically, those are those 8 combinations which we use as the data. And for those which has same ones and zeros, we use these codes. And we use those codes which has more transition between ones and zeros to ensure a good synchronization. And for those where we have to use the combination which differ in the number of the ones and zeros, then we have each time the option to select that one which lowers the integral difference. And then this A group is this one for the controls characters. And we have PCI Express version 1. It has a basic transfer or symbol rate of 2.5 2.5 giga transfer per second. It is not called the frequency because it is the number of bits. So basically the actual frequency which you can measure is only the half, because 1, 0, 1, 0 and so on. But so it is called a giga transfer. and it is for the single lane. You can compute that the capacity in bytes, when we encode them by 10 bits, is 250 megabytes per second, but due to some synchronization, headers, data checking signals and so on, the practical throughput of single link is something like 200 megabytes. But we can combine them by that lanes up to 16 independent lanes, and in such case we can get to the 4 gigabytes per second communication speed. Version 2 has doubled the communication or transfer per second frequency or symbol rate. Okay, I should be correct. So you can get to the 8 gigabytes per second of the raw throughput with the 16 links. Version 3 has found that the encoding of 8 to 10 waste in the fact 20% of the link capacity. For that reason, they have switched to the similar mechanism which encodes 128 bits of the data to 130 bits sent over the link. And this way, with the increase of the transfer rate to the 8 gigatransfers per second, we can get to almost the double throughput on the link. Then it has again increased the frequency by 2, or frequency, okay, I should not say frequency, the transfer rate. And this way we have almost 32 gigabytes per second. And version 5 goes to 33, but there are the changes that the symbols are not used only for the next generation of PCI. The symbols are not ones and zeros, but the encoding starts to be more complex. So it uses the mechanism amplitude, frequency, and so on, modulation of multiple bit into the single symbol. So it is, yes?
Can it have like not 0 volt and 1 volt? Can it have like 0.5 volts?
Yeah, but it gets to the that it is modulated in the frequency. If you know quadrature amplitude modulation, which is used for the video broadcast, if you have digital video broadcasting, DVT, terrestrial or cable or satellite, then it works such a way that you send the data at some frequency and you shift, basically you modulate by amplitude and by the phase shift. And usually the QAM allows to encode this is number of combination. So basically in the QAM 64 you are able to encode 6 bits into the single at the single instant of time. You need to keep that data for some time. It is not possible to basically immediately change, because you need to decode the actual frequency and phase shift. But basically this is what is used for the highest throughput through the air and so on. So in fact, these mechanisms are used for the Wi-Fi and so on. So today the communication even on the board of PC gets to the complexity to send the data over the air, because those very, very high frequencies in the fact are not delivered by the wires. I'm not sure if you know that, but physics prevents you to basically deliver very high frequency directly by the voltage level on the conductor, but it goes on as the wave between the poles, between the inside the corridor, in the fact which is which is denoted by the conductive materials. So, okay, so packet overhead is not included in that maximum transmission or capacity or bandwidth which has been used. So basically you need to compute with something like 20% less or something for the headers, addresses, CRC and so on. So it is something like on the Ethernet packet protocol. You have latencies with startup and so on. Switches are similar to the network switches, so it is switch network. And problem is that for those very high frequencies, basically you start with the A signal where you have a transition from the 1 to 0 and from 0 to 1. And as the link is longer and longer, then you have problem that at this moment you still can distinguish that those are ones and those are zeros. But at this moment, basically, you cannot find what are the ones and what are the zeros. You need to use some self-correction codes and signaling to resend the data and so on, because on those very high frequencies, the probability of some disturbance and error is relatively higher possibility and so on. If you look at the hard disk, then initial connection was analog in very, very old time, but then it switched to the parallel advanced attachment advanced technology attachment interface on the IBM PC-AT, which used parallel 16-bit bus. It was again limited by similar frequency, because on that parallel wires basically you get to some limit which is physical, where you cannot get to more than, in this case, 66 megahertz or mega watts on the link. So again there was a switch to that serial link with 8 to 10 encoding, which is the case for even the connection of the monitors. If you have HDMI connection, then it is using exactly the same encoding. Display port as well. USB has switched in the version 3 to encoding similar as well. So basically we need to switch from those parallel buses to those serial one. On the other hand, directly on the chip, we usually have parallel buses. Okay, so it is all for today's lecture. Maybe I will prepare some demonstrations. Lecture number 7. And if I go there, then you can see now we have some low frequency data. We send them on the left side to the link. And on the right side, we need to find the time when we can strobe. Now green. Now we can get blue and so on. If we go to the faster frequency, then you see that the delays in individual link allows now red, now green, but it is on the edge as you see. Okay, now for example, magenta and so on. And now when we make the frequency 2 times faster, then where we can take reds, greens? No, because at the time when it arrives, there is a mix. For whole time, there is a mix of the different data words. So, okay. So it is a demonstration why we need to switch to the serial. In the fact, parallel connection with multiple serial links, because we use this. And it allows to reconstruct the clock from the actual data signal. So this way, the clocks are not shifted against the data, which is a big advantage.
Basically, that's why all the traces have to have the same length.
In this case, it is not necessary. In the case of parallel bus, yes, because you need to have there the match between the clock signal and the data, and data has to provide the data corresponding to the given word in the sequence at the single time. But at the moment when you switch to the serial links, then it is no problem, because for each lane you reconstruct the clock signal separately. So basically, you have there the buffers which receive the individual bytes from the individual lanes, and then needs to recorrect them in the correct order. So you still need to know which byte is which, and if there is shift bigger than it is defined, but bigger than, I think, 1 byte time or a little more, then at this moment you are in the troubles. But it is 10 times later than for the parallel case. So you can go. And okay, then you end with the possibility to have two-level serial communication. So you need to switch to the multiple level, to that quadrature amplitude modulation and some other mechanisms. And this is even not enough. So then if you want to go even faster, then you need to switch to the optical fiber or some another kind of communication. So yes, it is the future.